So today what I want to do is I want to talk a little bit about some of the work we've been doing, looking at the value of forecasts, specifically subseasonal, seasonal hydrologic forecasts for robust and dynamic management of the water system in the Lake Ontario St. Lawrence River system, and particularly looking at dynamic management under climate variability and change. Before I get going, I want to recognize Kyla Semeninger, who was the student who did all the work I'm about to show you. She's now off to bigger and better things. And I also want to recognize the Great Lakes Adaptive Management Committee, who I'll talk a little bit about later, who cooperating with them on this project has been really great. And a lot of the results you see here come out of that collaboration. Okay, so when I was putting this talk together, I was trying to think how to do this for this particular crowd. And I thought there were three things that I wanted to cover. The first was, my thought was that the audience here might be pretty diverse. And so a bit of background on the Lake Ontario St. Lawrence River system might be a good place to start. So I want to sort of cover that first. And then after that, I thought it would be worthwhile to take a moment to talk about how we actually model this particular system and water systems in general, and how we try to think about optimizing the regulation of these big water systems. After I do those two things, I'll actually get to the topic of the talk that I had in the title, which is exploring the value of forecasts in system management. And particularly, we're going to be thinking about the value of forecasts in these big systems that are trying to meet many objectives all at the same time. Okay, so let's first go into a little bit of background on the Lake Ontario St. Lawrence River system. So for those who are unaware, although I'm sure most are aware, Lake Ontario is right here in north of New York, south of Ontario, Canada. And it's the last of the 5 Great Lakes, which flow from west to east. So Lake Superior down through to Lake Ontario, which then discharges out to the St. Lawrence River and then out to the Atlantic Ocean. And it turns out that there's actually a dam right on the St. Lawrence River, the Moses-Saunders Dam, which is operated by the International Joint Commission, or the IJC, which is this binational commission between the United States and Canada. And this dam has the ability to control, to some extent, the flows that are leaving and going down on the St. Lawrence, and then the levels on Lake Ontario. And the history of the system is really fascinating. And I was trying to think through the best way to sort of show this. And one way you can do that is by looking at a time series of the levels on Lake Ontario and then sort of seeing sort of historical events there. So that's what we're looking at on the top plot here of lake levels on Lake Ontario. And we're starting around 1918 all the way to around near present. And where I'll start the story, I'm going to borrow some figures on the bottom here from an IJC report. I'll start the story in the 50s. So in 1952, that International Joint Commission, the IJC, they issued what's known as an order of approval to build and operate a hydroelectric power plant on the St. Lawrence River. That's the Moses-Saunders Dam. And so they issued this in 1952. The dam actually eventually gets built, I believe, in 1958. So that's that little purple line there and that red line there. So they had the plans to put in this dam, and it was part of and linked to a larger project, the St. Lawrence Seaway Development Project, which was really looking to create a shipping channel from the Atlantic Ocean all the way through to the upper Great Lakes to facilitate commerce all the way into sort of interior North America. Now, around 1956, there were sort of in the early 50s, there were some very large flooding events that happened. And so in 1956, the IJC amended their original orders of approval to sort of expand the scope of the thoughts on this new dam project that they were going to put in, where now another goal that was being added, in addition to sort of supporting commerce or commercial navigation, as well as hydroelectric power, now they also talked about trying to compress lake levels to the extent possible, really to support riparians and reduce flooding. So the dam eventually goes in 1958, and they start regulating the system. They start regulating flows out of this dam. They often have names for their regulation plans. I'll be referring to a few of these. And an early plan that was used was called Plan 1958D. Early or mid 60s, there was a drought of record, really across the whole Northeast US. This included in influencing Lake Ontario, and we had record low levels. And so what they did is they made some large deviations to their management plan, their regulation plan, and eventually they started to regulate the system according to a plan which they called Plan 1958DD, or D with deviations. Okay, so then a few other interesting things happened. They started to regulate the system in the 60s with that plan, and they really continued to for a while. And as we move through the decades, a few sort of events of note occurred. One is that in the 70s, there was a significant amount of flooding under that current management plan, which caused a lot of damage. And then around the 80s and the 90s, there was a period of very stable water levels. And what environmentalists began to notice as lake levels really were stabilized for quite some time was that was having environmental effects, particularly on wetland communities around the coastlines of Lake Ontario. And a lot of the diversity in the wetlands around the lakes was being sort of taken over by these monocultures of certain types of coastal species here, these cattails, that were sort of taking over everything. And so there was an effort after a while to try to think through whether or not there could be an adjustment to the regulation of the system to try to increase some of the variability, the natural variability, back into lake levels to try to support some of those natural wetland species and other ecosystems of concern around the lake, while still trying to meet a lot of the other needs being met by that regulation plan, like commercial navigation and hydropower production and riparian needs upstream and downstream of the dam. So after a long process and a long legal process to develop potentially a new management plan, what came out of this long process was something that was known as Plan 2014. And Plan 2014 was this new regulation plan, and again, whose real attempt was to try to make releases from the system a little bit more natural, to try to sort of inject a little bit of additional natural variability into water levels on Lake Ontario for ecosystem restoration, while still meeting the needs of lots of other stakeholder groups in the Lake Ontario basin, as well as downstream on the St. Lawrence. And that brings us to the more recent years. So Plan 2014, which you can sort of think was developed and solidified in the year 2014, it really went into effect in the year 2017. And so this little box, this yellow box here, starting right around 2017, when this new management plan went into effect. So I'm going to zoom in on that. So here we're starting just in 2016 and then 2017 on, and we're again looking at water levels on Lake Ontario. And the dots on this plot are monthly average water levels on Lake Ontario across this 3-year period. The solid lines are sort of the monthly historical averages for water levels, as well as the maximum historical monthly water levels in that top light blue plot. And the thing that pops out is that here's that dotted line is where Plan 2014 went into effect right at the beginning of 2017. And then about 6 months later, there was a record-breaking flood on Lake Ontario in the year 2017. And then 2 years after that, that record got broken again, and water levels sort of exceeded what was previously the largest water level in over 100 years. So we have these two record flood events that occurred sort of right after this plan went into effect. It caused widespread damage around both the Lake Ontario basin, as well as downstream on the St. Lawrence River. And sort of maybe understandably, there was a really negative reaction to these flooding events. And there was a lot of blame put on that particular management plan. So there was a lot of, as some of these sort of news articles are highlighting, resentment that grew against the IJC and against Plan 2014 because the public was blaming the plan for all of this flooding, because the flooding happened right after the plan went into effect. In reality, there was a lot of analysis that was done where people were looking at this, and it really was probably just the weather. It was really, really wet, record-breaking wet. But the perception was that it was the plan. And so this led to a political response. So the New York Attorney General sued the IJC, saying they failed to implement their flood protection plans. And that drove, to some extent, the IJC to revisit Plan 2014. And I should say, when Plan 2014 went into effect, it went into effect with an adaptive management framework in place where they were going to review their plans on a 15-year rolling basis. And effectively what they decided to do is try to expedite some of that review in response to some of this sort of public reaction. Okay, so that's the background of this system. It's super interesting and sort of worthwhile I'll get into a little bit. What I want to do next is just talk about how we model systems like this, because I think this will help perhaps this audience understand the results of our looking at forecasting as I get towards later in the talk. So the first thing I want to talk about is just what really is a regulation plan. So for those who are not familiar with what I mean by that, I just want to sort of define that. A regulation plan is a set of rules that prescribes releases based on the state of the system. And so as a simple example of this, we have some state of the system, like the water levels on Lake Ontario and the water supply entering the lake. And then we have this regulation plan, or I might call it a control policy, which then dictates what the releases will be. And so to make this a little bit more tangible, I'm going to make up a little dummy made up control policy. So the policy I have right here, it's not actually a real control policy of the system, but it's useful for demonstrative purposes. So you can imagine a set of rules that says if the water supply entering the lake is above some threshold and the water level is above some threshold, then make some large release because your water levels are high and the water coming in is really high. Otherwise, make a smaller release, right? And obviously, this is not a real water control policy. And in fact, here's a little snippet of some of the code from the actual policy. The code is hundreds or thousands of lines of code long. This is just a little snippet. But I actually, if you just squint, want you to notice a bunch of ifs and elses in here. That's just to highlight that the basic structure of these if then else rules is very similar to this little dummy control policy I have here. So this one will do for our purposes. So we can simulate what the water levels in the Lake Ontario system would be under this given control policy. And we can do that with a simulation model. So here's our little dummy control policy up here. And I just want to show you like what that simulation might look like. So here we have water supplies entering Lake Ontario, water levels on the lake down here. And over here on the right, the outflows or releases from the lake. And so I'll look at my little rules and I'll put the thresholds that determine the rules on this plot. So here's 9,000 CMS for the water supply and 247 feet for the thresholds on water levels. And now what I'll do is I'll literally walk through time step by time step at how a simulation would work. And I'll start here with one on the first time step where we have a water supply, let's say 8,500 cubic meters per second. The water level starts at 246.5 feet. Those are under the thresholds of these rules. And so we would release 8,000 CMS, and that's over here. Now the incoming water is around 8,500. That's more than what's being released. So that means the in is bigger than the out. So the water levels are going to go up on the next time step, like they did right here. And we can keep on marching through time like this. So we're still under our decision thresholds for water supply and water levels. So we can still release 8,000, go to the next time step. Now our water supply, it keeps on rising. We're over the 9,000 CMS threshold, but our water levels aren't also over 247. So this little and condition isn't being met. So we're still going to release 8,000. And then finally, once both water supply and water levels get over those trigger thresholds, now we'll start releasing a lot of water, 10,000 CMS, and that's going to start drawing our water levels down as we move through the simulation. Okay, so that's basically how a simulation model would work, how we would specify a control policy and then simulate what that does for releases from the system and then water levels in the system. Okay, so now we can kind of hopefully understand how we can specify a set of rules about how to make releases from this big water system. Now the question is, how does that regulation plan influence the people and the ecosystems who live around the lake and the river? So what we need to do is come up with some mapping for how water levels and flows in the system are going to benefit or harm different interests. So we have our Lake Ontario levels that we can simulate. We have flows on the St. Lawrence River we can simulate. And we want to know, what does that mean for instance, flood risk for people who live upstream of the dam, flood risk for people who live downstream of the dam on the St. Lawrence River, the commercial navigation industry, and then a bunch of other stakeholder interests like hydropower production, wetland health and services, water supply needs, and also there's a recreational boating industry. So I just want to talk a little bit about how we would actually create that connection. And to do so, we use what's known as performance indicators, or PIs. And these are models that relate water levels and flows to societal and ecosystem impacts. And I'll just give you one example of what one of these PIs can look like, and I'll do it for flooding on Lake Ontario. So if we wanted to try and create some mathematical relationship that lets us get a sense of flooding impacts due to this regulation plan, what we can do is, as an example, we can go all around the Lake Ontario shoreline, and I've zoomed in to one little area of the shoreline. And we could, for instance, find all the building parcels that are on that shoreline. We could pick off the elevation at the base of each of those buildings. And then we can come up with a relationship that says something like, for different water levels on Lake Ontario, how many homes would have the water sort of at or above the foundation of the home? So the number of homes impacted at different lake water levels. And this might vary for across seasons, because in some seasons like winter, there might be more storms and windiness. And so in addition to just like the static lake level, you might get more wave activity or storm surge that you want to account for. And so you can have sort of different relationships across seasons. But this is a way to try to come up with like a quantitative measure of impact for a given interest sector based on our simulation modeling of water levels and flows in the system. And we can try to do this for all of the different impact sectors that we're interested in, the ones I listed before. Okay, so now, what we want to do in this project is we want to understand how we can identify alternative regulation plans of the Moses-Saunders system, particularly regulation plans that are going to use forecast information in different ways, and to try to do so in a way that benefits all of those different interest groups. And so I want to talk a little bit about how we would actually find those candidate regulation plans. And I'll do so again by using my little dummy control policy I used at the beginning. And when I put this out there, I had these numbers, these thresholds that would trigger different releases. And I'd have these numbers for the particular releases. And really, like, where did those numbers come from? Some engineer made some decisions and decided to put these thresholds in here. But really, they could be different. So you can imagine that each of these numbers could be considered a dial. And we could change the dials back and forth and change all of these numbers. And every single time we change these values, we would have a totally different regulation plan. It'd be a totally different control policy. The problem is there's an infinite number of combinations of dials that you could try out. And it's very difficult for a human to sort of work with all of those. And so it's very different for people to really test out all possible regulation plans. And so as part of this project, what we're going to be using is this optimization procedure. It's a many objective optimization algorithm. And basically what it does is we're going to be using a simulation model where we simulate the system for a given control policy. We see what it means in terms of system performance. And then there's going to be this optimization algorithm that messes around with those dials really, really quickly and sees if it messes around with the dials one way or the other. Do we see improvements in different of these performance indicators for these different stakeholder sectors? Now, the complicated factor here is what you're going to get is sometimes you're going to be able to improve performance for some of these performance indicators, and you're going to get reduced performance for others because there's going to be conflicts. And so the optimization algorithm we're going to use is going to try to identify all possible regulation plans, including the ones where you have very interesting conflicts between different objectives. So just to give you a sense of how this is going to look and how we can visualize this, I'll use a plot that looks like this. And so what we have here is our different stakeholder interest groups: upstream and downstream flooding, commercial navigation, hydropower, ecosystem health, and recreational boating. And I'm going to start putting lines on this plot. Each line is going to be a different regulation plan. And all you really got to know is that if the line is higher on this plot, it means it's better for a particular stakeholder interest. And what I'll do is I'll first put on the status quo plan of this system, which is Plan 2014. That's the current regulation plan. And so this is really like one set of dials for those decision variables in the regulation plan. And now what the optimization algorithm is going to do is it's going to identify alternative plans that perform differently, but optimally in some way across all of these different objectives. So for instance, the optimization algorithm might identify this set of dials that does worse for upstream flooding, but does better for downstream flooding and commercial navigation and hydropower, does worse than the status quo for wetland health, and a tiny bit worse, but really the same for recreational boating. But the optimization is also going to identify other alternatives. It might identify a second alternative that has a whole different set of like better and worse trade-offs across these different objectives. And in reality, what the optimization actually produces is not just one or two or three alternatives, but a whole set, often hundreds of alternatives that we can look at. So each of these gray lines is a plausibly interesting regulation plan that we might want to explore for managing this system. Now, this is a lot of regulation plans, and it's a big old messy, plot of gray lines to understand anything. So really what we need to start thinking about is which of these plans actually represent interesting trade-offs and opportunities for alternative regulation of this system. And the way we can think this through is thinking about screening those regulation plans by thinking about how we want to actually balance different objectives in the system. And so there's a lot that needs to go into this, and there's actually a regulatory framework for thinking about this in the Lake Ontario St. Lawrence system. There's a Boundary Waters Treaty of 1909, which sets out a bunch of guidelines, I would say, about how to think about which objectives sort of need to be thought about first and which objectives should be thought about second. And there's a lot of debate around that. But to summarize it quickly, water for water supply, for commercial navigation, and for hydropower, in that order, kind of needs to be considered first. But a lot of the other interests also sort of in the treaty, there needs to be suitable and adequate provision for their protection and indemnity, as the language goes. That's actually kind of vague in my opinion what that means. But the point is that when thinking through regulation plans, they need to adhere to this treaty. And so that you need to think through, are you really sort of putting some of these interests first? And then also, are you sort of providing adequate protection for some of the alternative interests as well? So anyway, to sort of, for that big set of regulation plans that the optimization produces, trying to think through how we can sift through them. And with that treaty in mind, what we can do is create some satisficing criteria that says, are these regulation plans actually meeting what we think would be plausible standards of regulation that adhere to that treaty? And there's a couple of ways we can do this. There's lots of ways we can do this. And I'll show you results for one set of satisficing criteria that we created. And the way we did it is we sort of said, okay, compared to the current plan, Plan 2014, we really only want to look at regulation plans that meet certain standards. Number one, we're really only interested in ones that have no worse flooding, given all the recent flooding problems in the system. They really can't have any worse commercial navigation, kind of because of the treaty. They can only have slightly worse hydropower, maybe around the hydropower being produced under that old plan, 1958 DD, again, sort of to adhere to that treaty. We don't want to see any worse ecosystem performance because Plan 2014 was trying to improve the ecosystem, so we don't want to give that up. Maybe we'll entertain moderately worse performance in recreational boating, though, and that would be deemed as okay. And so if we set those sort of criteria as which policies we think are plausible alternative regulation plans, then only those blue ones that I have highlighted here actually would meet all of those standards. Okay, so that's sort of like how we're approaching modeling and trying to identify alternative regulation plans in the system. Now I actually want to get to the experiment that we conducted, which is trying to identify alternative regulation plans that use forecast information to improve the management of this system. And there's really two specific research questions that we were asking in this effort. The first is just what is the relationship between the value of the forecast for management and attributes of the forecast, and by attribute, I mean lead time and skill, in a many objective system. And then, can forecast-informed operations adequately meet basin needs in a many objective system, particularly as the climate is changing? And does that depend on the attributes of the forecast themselves? Okay, so I'll sort of go over the experimental design that we used to explore this. And what we did is we created different forecasts of water supply entering the Lake Ontario St. Lawrence system. And we created forecasts at 4 different lead times because we were interested in whether or not lead time makes a difference here. And so we created 12-month ahead forecasts, 6-month forecasts, 3 months forecasts, and 1-month forecasts of water supplies. And for each of those 4 lead times, we created water supplies at 2 different levels of skill. What I'll call the status quo level of skill, which is about the level of skill that current forecasting technology has right now, as well as a perfect level of skill, so perfect foresight. So we have 4 lead times and 2 different levels of skill, so 8 different forecasts altogether. And for each of them, we put those forecasts into that multi-objective optimization that I talked about previously to develop plausible new regulation plans, optimal regulation plans that are tailored to each of those different forecast sources of forecast information. And then we use those satisficing criteria that I talked about before to really zoom in on specific interesting regulation plans tailored for different forecast leads and forecast skill levels. And then for those particular candidate policies that we thought were really interesting and met those satisficing criteria, what we did is, I should say, all of those policies that were trained only using historical water supply data. And then we take those candidate policies and we reevaluate them under many, many different future plausible water supply scenarios, many of which reflect climate change scenarios that are possible, as well as just other sort of sequences of plausible climate and hydrologic variability that could impact the system. Okay, so what I want to do now is show you the results of sort of the experiment. I'm only going to highlight sort of the primary results that I think are the most interesting for the take-home punchline of the results. So we're looking at one of those plots that I showed before, where we're looking at for different objectives along the x-axis there. We're looking at the performance of a bunch of different policies. So what we're going to focus on first is for one lead time, the 12-month lead. Again, we have 4 different lead times, but for now, I'm just going to focus on the 12-month lead. We have a bunch of different policies that I'm showing you on this plot. So each line is a policy. That red line is the Plan 2014 baseline policy. All of those gray lines are all the policies that the optimization identified. And then we have these 2 different colorings, and I'll focus first on that light blue. These are policies that the optimization identified using a 12-month ahead forecast at a status quo level of skill that also met those satisficing criteria. So these are all interesting policies, like plausibly good policies from a regulatory standpoint, that are using status quo levels of forecast skill. And then those dark blue lines are optimal policies identified by the algorithm that are meeting those satisficing criteria, but they use perfect forecast information, which isn't realistic, but we're just interested in what happens if you give the system sort of perfect forecast information. And we're looking at the performance of all of these for our 6 different objectives. And for all of these objectives, the higher the line is on this plot, the better it is for doing for that objective. So there's really 2, I think, particularly interesting results that pop out here. The first is for some objectives, we see results that we might expect, which is that if you give the system perfect forecast information, so we're looking at the dark blue, you can probably do better in certain objectives than if you give it less good, less skillful forecast information, which is like that light blue. And that's particularly the case here we see for downstream flooding and flood risk on the St. Lawrence River. But what was actually more interesting is that you don't see that for many of the other objectives. So for instance, if you look at, as an example, hydropower or wetlands and recreational boating, you really can't separate the 2 different blue colored lines, which sort of suggests that even if you gave the system better forecast information, you weren't necessarily seeing improved and satisfying performance across all of the objectives that you were considering in the analysis. Okay, this was all done at the 12-month lead time. So what I'll do now is just zoom out a little bit. I'm going to show the same plot, but now across all 4 different lead times that we were examining. So we have 12-month, 6-month, 3-month, and 1 month. So here, I'll just highlight 2 points that I think are particularly interesting. The first is down below, the 3-month and the 1 month. These are shorter lead forecasts. And if you look, you'll see that you don't actually see many light blue lines, if any. You see 1 on the 3-month and none on the 1 month. What that's telling you is that if the system is working with status quo forecast skill, so like current levels of forecast skill, and they're using short lead time forecasts, the optimization couldn't or could barely identify any regulatory policies that use those forecasts that meet the satisficing criteria for all of these different objectives. And that's particularly interesting because those shorter lead forecasts actually tend to be more skillful than the longer lead forecasts. It's harder to predict things farther out in time. So the short lead forecasts are actually usually more skillful, but still the optimization couldn't actually identify satisficing policies with that information. So because of that, I'm actually going to focus the rest of the analysis more up here on these longer lead forecasts. And what we're going to do is we're going to just pick 2 policies to focus on, one from the 12-month and one from the 6-month. And we're going to zoom into those because everything I've shown you so far has been evaluating these policies under historical water supply conditions. I'm going to take these 2 policies right here and then look at their performance under lots of alternative future climate conditions. And I'll do that on the next slide. Before I jump there, though, I'll just make 2 quick points. One, if you squint and you compare the yellow line under the 12-month to the yellow line under the 6-month, you'll see that this 6-month policy tends to be a little higher on most of the objectives in the 12-month policy under historical conditions. So the 6-month policy tends to do a little bit better under historical conditions. And the other thing I'll mention, similar to the 3-month and 1 month, the 6-month forecasts themselves under status quo conditions, they tend to be more skillful. They have like lower root mean squared error than the 12-month forecasts, again, because they're sort of shorter lead time forecasts. I bring that up because it's going to be that's an interesting point in comparison to the results that I'm about to show you. So now what I'm going to do is I'm going to jump to the next slide. I'm, for the moment, just going to focus on this 12-month forecast policy. So just this one right now. So we're only looking at that 12-month status quo forecast policy. And what we're looking at is how that policy performs for only one objective, the ecosystem health objective at first. But now we're looking at the performance not just under historical climate conditions, but under many, many alternative water supply conditions. So what we've done is along the x-axis here, we've ordered 660 different future water supply scenarios. And on the left are the drier ones, moving to the right, which are the wetter ones. The historical one is this black line right here. And for each water supply scenario, it's either red or blue. And if it's blue, that means that that policy that I selected met the satisficing criteria for that ecosystem health objective for that particular future water supply scenario. And so when we look at these results, what we see is that there's a lot of blue. So this policy is doing reasonably well for many future possible states of the world, future hydrologic conditions. Although if things get really, really dry, this policy begins to perform poorly. It doesn't meet that satisficing criteria for the ecosystem health objective, okay? So what I'm gonna do now, I'll flip to the next slide where instead of just showing you ecosystem health, I'll show you the other objectives as well for this policy. So this is the exact same plot. Here's that ecosystem health objective that we were just looking at. But now we're looking at all the other objectives too, like upstream flood risk, downstream flood risk, commercial navigation, hydropower, and rec boating down here. And the take-home message that that I see on this plot is largely there's a lot of blue. So this particular policy is really robust. It's got a lot of satisficing performance for lots of different future water supply conditions, both dry and wet, for most objectives. With a little exception, if things get really wet, you see a bit of flooding issue, but overall very blue. And really, this stands in stark contrast to now if I show this result in comparison to the same result, but for that 6-month policy that I highlighted before. So I know that the plots have been a bit squished here, but this top plot is the exact same plot I was just showing you for the 12-month policy. What I've added here is the 6-month policy. I'm showing the results for that down here. And what you see there is you see a ton of red. So that 6-month status quo policy, which I'll remind you, performed a little better historically, and the forecasts tend to be a little more skillful at that shorter 6-month lead time. The policy we identified actually turned out to be a lot less robust for several objectives under a broad range of future climate conditions. Okay, so I'm going to try and wrap it up here so we have time for questions and just summarize what I think some of the key findings are. The first is that subseasonal and seasonal forecasting, I think, can help a water system navigate trade-offs between many objectives under future conditions. I think we saw that with that 12-month policy that showed a lot of robust performance across many of the objectives, across many different sort of future hydrologic conditions. However, better forecasts and better forecast information in terms of skill does not always improve many objective performance, particularly as climate conditions change and you need to sort of consider robustness across a wide range of possible futures. And one thing that I didn't get into for sakes of time, but I'll just sort of highlight here, we dug a little into why we were seeing some of the results we were seeing, why better forecasts weren't always leading to better multi-objective performance. And there's really two major things that stood out to us. The first is overfitting. When we were doing all that optimization, we were always optimizing to the historical water supply conditions and then testing our policies under a bunch of other future conditions that hadn't seen. And when you give policies really good forecast information in the historical condition to fit to, they tend to overfit to those really good forecasts because there's very little uncertainty in them. And that actually makes the policies sensitive to different sort of sequences of future hydrology, even if they're given really good forecast information in those future conditions. And then the second bit is that there's just really complicated dynamics between the different objectives, the constraints of the system, and actually how we formulated the control policy itself and how it uses forecast information. And some of that complicated dynamics is also sort of behind some of these sort of interesting and non-intuitive results. So I think I'll leave it there, and hopefully we have maybe about 10 or 15 minutes if there's any questions.